Hi friends, Dr. Jim Daly here. Welcome. I'd like to talk to you this afternoon about something that's made some headlines in much of the press as of late. It has to do with one of the most celebrated scientists of all time. Well, actually two of the most celebrated scientists of all time, Isaac Newton and Albert Einstein. As we know, Newton left this world in 1727. He published his great work, Principia Mathematica, in 1687. And he basically, his work and the math he developed, calculus and his laws of physics and the universal law of gravitation, basically described the universe in its best way, as best he could, given the constraints, the prevailing constraints from that time upwards until the beginning of the 20th century, when Einstein basically published or developed his new theory of gravity called general relativity. Newton never claimed to describe any of the whys of gravity. He just described the effects, the phenomenon itself, by the use of mathematics, calculus. He developed calculus as a way to describe nature as most accurately as possible. And without calculus, you really can't. Okay, you can approximate it using some advanced techniques in algebra, etc., but you need calculus to actually describe things like instantaneous velocity. If you drop a rock, for example, from a height of 1 meter, you can calculate the average speed from top to bottom when it hits the ground. But in order to calculate the instantaneous velocity at any given point along that path, you would need calculus. So Newton's mathematics, Newton's laws of gravity, his 3 laws of motion, basically described the world and the universe with a remarkable degree of accuracy. And it was the standard. In fact, it's still taught. Newton's classical dynamics is still taught in all undergraduate physics courses. There's some research that's either concluded or it's in its final form to be published very soon concerning a topic that has also been in the news lately as well, that of black holes. Okay, for example, back a while ago, well, a few months ago, there was an image taken with with what we call the Event Horizon Telescope, wherein the entire surface of the entire diameter of the Earth was used as a giant radio telescope. And what we did was, using the wave nature of light, we combined the output of individual radio telescopes across the surface of the Earth to produce an image of a black hole at the center of the galaxy Messier 87, and that's it right there. Okay, if we take a look at this, zoom in on it a bit. Here's the sun, that little point right in the middle. That's the orbit of the sun. This is to scale. If we were to superimpose the solar system on top of this, this is how it would look. So the orbit of Pluto is here, and the furthest craft that humankind has ever built and launched into space, Voyager, would be about here. So this distance here is what we call the event horizon of the black hole. Now, this particular black hole is tremendous. It's 55 million light years away. In other words, the light we see from this has taken 55 million years to get here. And the mass of that black hole is many billions of masses of the sun. This is our article we published describing this remarkable discovery. This was a worldwide phenomenon, and what we did was we imaged the event horizon of a supermassive black hole 55 million light years away. Now, this was a verification of Einstein's general theory of relativity. And I'm basically describing these things as a backstory that's going to lead up to the general topic of this video. The black hole at the center of our own galaxy was also a target of this study, and that's not discussed here in this article, but it's part of the entire study. Okay, the black hole at the center of our own galaxy is the topic of this latest research I'm going to talk about in a moment. Okay, so the mass of the black hole at the center of M87. Again, this is on the order of about 3.5 billion times the mass of the Sun. Okay, that's almost an inconceivable amount of gravity, whereas the mass of our own black hole, the center of our Milky Way, is approximately 1,000 or 3 orders of magnitude smaller, at about 4 million times the mass of the Sun. Okay, so fast forward to recent studies published in the journal Science for July 25th by Andrea Ghez. Okay, she published this study describing the star known as S02, the star that orbits the black hole at the center of our galaxy. Yeah, let's zoom in on this. Okay, here's the center right here. That star indicates the center. That's where the black hole is. Here's SO2. Here's SO1. Now these are the orbits of these stars. This SO2 has a 16-year orbit, and we're able to use Newtonian dynamics to calculate the orbit and plot its trajectory and so forth. But there are certain aspects to the orbit that can only be described using Einstein's theory of relativity. And we knew that, Newton knew that in 1687, excuse me, when he published Principia. He knew that there were certain phenomena that his theory just simply couldn't explain. He knew about the orbit of Mercury not being described quite right back then. We knew this all the way up through Einstein knew this. And one of the first tests of his theory was to test the orbit, the prediction that Mercury's, you see, every object that orbits another object orbits in a circular, with an elliptical orbit. There is no such thing as a circular orbit. Because it's an ellipse, there is a point in the orbit where it's furthest away and closest. The closest point is called the perigee. The perigee of Mercury's orbit precesses, means it changes ever so slightly every 100 years or so. Okay, by a very tiny amount, which could never be described by Newton's laws of gravity, because they looked at the world in a completely different way. Okay, and he knew that, Einstein knew it. So Einstein knew about Mercury, he knew about all these, that is one phenomenon. Another phenomenon, which is the subject of an article we've published in our news and articles section of our public website, is on May 29th, 1919, the total eclipse of the Sun was observed by Sir Arthur Eddington. Airy was the astronomer royal at the time, but it was Arthur Eddington who actually made the observation and the discovery. He went on the expedition, he observed the eclipse, and compared it to the observation of the sky in the absence of the Sun and the positions of the stars. The difference in those positions, the perturbations or the change in position of those stars, was consistent with Einstein's theory of relativity. It's Sir Arthur Eddington. He calculated the calculations of positions of the stars close to the Sun, with the Sun present and with it not, in a different part of the sky or not at that moment. The positions of the stars changed according to the Sun's gravity, and that change, the perturbation in the position of those stars, was consistent with what was predicted with Einstein's general theory of relativity. And every test from that point to the present day has always confirmed Einstein's general theory of relativity. So that brings me to what I want to talk about more generally today. This is we opened this video up with, depicts a star, or a black hole rather, or a massive object, could be a massive star, warping the what we call the space and time in the vicinity of that star. Now, that idea, that concept is an abstraction. Okay, I don't think anybody can really truly imagine what this would look like in 3 dimensions. But consider a sheet of rubber or a sheet of nylon. You place an object with any given mass on top of it, it's going to warp the sheet, yes? Okay, so that's the model, that's the abstraction we're working with. Einstein suggested in his general theory of relativity that that idea is what describes the gravitational force that exists, between 2 objects that have a given mass. Okay, that the object's mass will, warp or distort the smooth fabric of space and time, and any object will be constrained to travel along that space and time and conform to the curvature of that space. This is an abstract idea, and it's difficult to imagine, but that's what Einstein imagined. And to this day, every test, starting with the test back in 1919, May 29th, 1919, has consistently proved Einstein to be accurate. Now, Professor Ghez, she was conducting these studies at the W.M. Keck Observatory on the large island in Hawaii, Mauna Kea, with the twin 10-meter telescopes on the large island. And for now, she says, this is her comment here, that Einstein's theory, after 100 years, is beginning to fray at the edges, but it's okay now. Einstein is right, at least for now, she says. We can absolutely rule out that Newton's law of gravity, our observations, are consistent with Einstein's theory of general relativity. However, his theory is definitely showing vulnerability, and she doesn't elucidate on what that means. There has been a lot of people, very smart people, that have come along and claimed that Einstein's theory has some weaknesses and so forth. But until someone comes along and can publish another theory of gravity that describes the universe the way Einstein's theory does right now, then these people should learn a little bit of humility and not be so, basically have so much confidence that Einstein, that they're on an equal or on a par with Einstein. Okay, these people should have a little bit more, in my view, they should have a little bit more humility. For her to come out and claim that his theory is definitely showing vulnerability, it cannot fully explain gravity inside a black hole, and at some point we will need to move beyond Einstein's theory to a more comprehensive theory of gravity that explains what a black hole is. Einstein was very clear. Okay, his theory on relativity has worked thus far consistently for 100 years. And although her theory, Gez's, well, not her theory, her observations and her work, her recent study published, is laudable and commendable, there's a certain arrogance to it that's kind of, that's distasteful and doesn't respect the long history of how we came to understand the universe, Einstein's contribution to the understanding of the natural universe, and so forth. Okay, the long and short of it is this. We take a look at this here. Look at this spinning object. This is an object of any given mass moving through space or orbiting another object at its center. And you can see in 3 dimensions what it's doing to the surrounding space. Okay, so that's more or less the idea of what Einstein was suggesting. Now, we go a little bit further and take a look at one of his original equations here. This is what we call the Einstein's field equations. It's a tensor expression. Tensors allow for physical systems to be described in a coordinate independent manner. In other words, if you're talking about a spherical surface or a cylindrical surface or a basic Euclidean surface, a 3-dimensional square and so forth, you don't need to define the parameters of the particular geometry. You can define it universally, okay? This expression describes what is known as a gravitational inertial field, the interplay between the curvature of space and the distance along the curve formed on what we know as the space-time fabric. Okay? That's on the left side, or this expression right here. Okay. On the right side of the equation is the source of the gravity, or the source of the curvature here. This is Einstein's, or excuse me, the universal gravity constant, and so forth. This is 8 pi g, and this is another tensor here. Okay, so this is Einstein's original field equation, and it's been pretty good. In fact, another aspect of his special theory of relativity, beg your pardon, his general theory of relativity, we use in the technology everybody's come accustomed to using these days. Mobile phones, GPS, the geopositional system, the GPS system that everybody uses to locate things within an accuracy of a couple of meters on the surface of the Earth. Without Einstein's general theory of relativity, that would not be possible. So we've come to use his theory pretty much, or come accustomed to using technology that was developed because of his discovery and because of his understanding of the universe and what he's described as pretty much as our general life. Now, for her to come out and just say that that Newton was wrong is really not. Again, it to me speaks of a certain hubris and a certain arrogance that's really distasteful at this point. Okay. We can absolutely rule out Newton's law of gravity. There was never any suggestion that Newton's law of gravity could describe what they're observing at the center of these massive objects, these black holes, which, by the way, are the result of the end state for an individual black hole is a result of the collapse and utter destruction of a large massive star. But these massive black holes at the center of the galaxy and other galaxies are the agglomeration of black holes that have come together and merged. Okay. My only comment here, I'd like to just report that this study is available in the July 25th edition of Science magazine, right here. If you want, this is the URL, you want to link to it. It's right here. We're going to put a link to this in the description below. You can link to the full text right here and read it. And her comment, her studies published here, Andrea Ghez. I would just say, Andrea, you should learn a little bit of humility when you start making comments about the accuracy of a theory that's been pretty accurate for 100 years. Okay. So I'm going to break here, ladies and gentlemen, friends. All the information that discussed, the links to these various sources, perhaps you'll be able to find in the description below. And our public website is astronomyforchange.org, and we publish news and articles of general interest and topical stories of relevance, such as this one, in our news and articles section, our latest stories. Okay, everybody, until next time, please do like and subscribe, like and share, rather. And if you're not already subscribed to our YouTube channel, please do so, because that's a separate subscription compared, not included in the subscription to our public website. Until next time, everybody, thanks for watching, and please keep looking up.